Algebraic structures, Lecture 1. Groups and subgroups. Let us start with the definition of a group. Definition. A group is a tuple which consists of a set G, a binary operation on G, usually denoted by dot, and the fixed element E of the set G. This datum is supposed to satisfy the following axioms. First of all, the operation should be associative. This means that for all elements A, B, C in G, multiplying A with the product of B and C gives the same outcome which we get when we multiply the product of A and B with C. The next axiom says that the fixed element E should be an identity element, which means that for all elements A in G, the product of A and E, regardless on which side, should be equal to A. And finally, the third axiom says that for each element A in G, there should exist an element B in G such that both A times B and B times A are equal to the element E. Here are some remarks. First of all, the tuple consisting of G, the operation dot, and the element E is quite often denoted simply by G. Then the product of A and B is usually simply written by AB without the dot in the center. This is when the operation is clear. Also, the identity element is sometimes called the unit element or a neutral element. Also, a nice remark is that the set G is not empty. Any group is a non-empty set because it contains this fixed element E. And also one small disclaimer: if the operation in the group is some kind of addition, then the fixed identity element is usually denoted by 0. Here are some basic examples. First of all, the singleton set G, which consists just of the identity element, with the trivially defined operation where the identity element times itself gives the identity element, this is a group. And all axioms are just obvious because everything is uniquely defined. Example 2. Consider as a set G is the set of all integers, as our binary operation, addition of integers, and as our fixed neutral element, the integer 0, then again we get a group, the additive group of all integers. And again, the associativity and unitality here are obvious. They are the standard properties of the addition of integers. And the inverse of an element A is the opposite integer minus A. So for addition, the inverse is usually called the opposite element. And exactly in the same spirit, the set of all real numbers with respect to addition and with the neutral element 0, and the set of all complex numbers with respect to addition and with neutral element 0, they are also groups. Next example. Consider as a set G the set of all non-zero rational numbers. This is usually denoted by Q star. As our binary operation, consider the multiplication of rational numbers, and as the identity element, consider the rational number 1. And then again, associativity and unitality here are the standard properties of the multiplication of rational numbers, and the inverse of A is 1 divided by A. So this is really the inverse of A. Note that we have excluded 0, so indeed any non-zero rational number has an inverse. So we get a group. And similarly, all non-zero real numbers with respect to multiplication and with the identity being the element 1, this is a group, and all non-zero complex numbers with respect to multiplication and with the identity element being the complex number 1, this is a group. Example 6. So this is a negative example. If we take all non-zero integers with respect to multiplication and with the identity being the integer 1, this is not a group because the third axiom is not satisfied. For example, the integer 2 does not have an integer inverse. It does have an inverse in the set of all rational numbers, 1 divided by 2, but 1 divided by 2 is not an integer, so if we consider the set of all non-zero integers in this set, the element 2 does not have an inverse, and therefore this is not a group. Now let us talk about basic structural properties, and this will be addressing the uniqueness of the unit and of the inverse. Let us start with the uniqueness of the unit. Proposition: let G be a group. Let E tilde be an element in G, which has the properties that E tilde times any element A is equal to A, and A times E tilde is equal to A, for any element A in G. Then E tilde is equal to the identity element E, which is the element in the definition of the group G. So the identity element of the group is unique. Proof: let us take the product of our element E and the element E tilde. On the one hand, this is equal to E tilde because E is the identity element. On the other hand, this product is equal to E because of this property of E tilde, that E tilde is an identity element. And therefore E is equal to E tilde. And this completes the proof of this proposition. Next, let us establish uniqueness of the inverses. So let G be a group and A a fixed element in G. Let B and C be two elements in G such that B times A is equal to A times B is equal to the identity, and C times A is equal to A times C is equal to the identity. Then B is equal to C. So the inverse element to A is unique. So let us prove this. Let us compute the product of B with the product of A and C. On the one hand, the product of A and C is equal to E, so B times C is equal to B. On the other hand, the product of B with the product of A and C is equal to the product of B and A times C. So here we use the associativity of our operation. The product of B and A is E, and E times C is equal to C. And this implies that B is equal to C, and proves uniqueness of the inverse element. So since the inverse element is unique, we can introduce a notation for it, and the inverse element to A is usually denoted by A to the power minus 1, A inverse. Again, a disclaimer: if the operation in the group is addition, then the inverse element of A is usually denoted by minus A and is called the opposite element. Let us next comment on the inverse of the product. Proposition: if G is a group and A and B are two elements in G, then the inverse to the product of A and B is equal to the product of the inverse of B and the inverse of A. Note that the order of factors is reversed. Proof: let us try to compute the product of A and B with the product of B inverse and A inverse. So we will use the axioms of the group. First of all, we use the associativity to rewrite this product in the following order. So we first multiply A and B, then we multiply the outcome with B inverse, and then we multiply the outcome with A inverse. Next, we use the associativity to move the brackets here. So we rewrite this in the following order. We first multiply B and B inverse, then we multiply with A on the left, and then with A inverse on the right. The product of B and B inverse is E, so this is equal to A times E and then times A inverse. The product of A and E is A, and so we will get A times A inverse, and this is the identity. So the product of AB and B inverse A inverse is the identity. A similar computation shows that the product in the opposite order, if you multiply B inverse times A inverse with A and B, this product is equal to the identity. And therefore, the claim of the proposition follows from the uniqueness of the inverse. So we can compute the inverse of the product of two elements in any group. Okay, let us now discuss more advanced examples. And the first one will be example of the so-called symmetric group. So let X be a set. Denote by S sub X the set of all bijections from X to X, all bijective functors from X to X. Let IDX be the identity function on X, so that's a function which does nothing. It sends an element A in X to itself, to this element A. And consider the usual composition of functors. That's the associative operation on functions. Then the claim is that the set of all bijections from X to X with respect to composition of functions and with the fixed element the identity function on X is a group. And indeed, composition is associative, the identity element is a unit with respect to composition, and all bijective functions have inverses. That's exactly the point of being a bijective function. And this group Sx is called the symmetric group on X. Note that if X is the empty set, then an Sx contains just the identity element. And if X is a finite set consisting of the numbers 1, 2, and so on up to n, where n is some fixed non-negative integer, then S sub X for this X is usually denoted by S sub n. Next example is the example of invertible matrices. So let K be either the set of all rational numbers, or of all real numbers, or of all complex numbers. Let n be a non-negative integer. So we denote by GLN the set of all invertible n times n matrices with coefficients in K. Let E be the identity n times n matrix. Then the set of all these invertible n times n matrices with respect to the usual matrix multiplication and with the identity n times n matrix as the identity element, this is a group. And all axioms follow directly from the basic properties of matrix multiplication. And the terminology, so it's GL, means the general linear group. So this is usually called the general linear group over K. Next, let us talk about subgroups. Let G be a group. Definition: a subgroup of G is a subset H of G which inherits from G the structure of a group via restriction. This means the following. First of all, the identity must belong to H. Second, for any pair of elements A and B in H, their product in G also must belong to H. And finally, for any A in H, the inverse of A in G must belong to H. So H is closed with respect to identity, with respect to products, and with respect to taking the inverse. And the notation, so this is a notation which says that H is a subgroup of G. Note, the condition that E belongs to H can be changed to the condition that H is a non-empty subset of G. Indeed, in one direction, if E belongs to H, then H is not empty. So let's prove the opposite. So assume that H is non-empty and the two other conditions are satisfied. Take any element A in H, then by the third condition, the inverse of A belongs to H, and by the second condition, the product of A and its inverse, which is the identity, must belong to H. So, having this second and the third condition, the first condition can be replaced by H being non-empty. And again, by definition, any subgroup is a group on its own right. More or less by the definition, it inherits. So any subgroup inherits from the original group the structure of a group. Here are some examples. First of all, the additive group of integers is a subgroup in the additive group of all real numbers, which in turn is a subgroup in the additive group of all complex numbers. Example 2. The multiplicative group of all non-zero rational numbers is a subgroup in the multiplicative group of all non-zero real numbers, and that, in turn, is a subgroup in the multiplicative group of all non-zero complex numbers. Next example. Any group has itself as a subgroup. That's an obvious claim. Example 4. Any group has a subgroup, a trivial subgroup consisting just of the identity element. That's because the identity times the identity is equal to the identity, so in particular the inverse of the identity is the identity. Example 5, and this is a negative example. The set of all non-negative integers with respect to addition is not a subgroup of the set of all integers with respect to addition. So we have the additive group of all integers, and inside we take non-negative integers. So this contains 0, and this is of course closed with respect to addition. But it is not closed under taking the inverse or opposite elements in this case. So this is not a subgroup. Example 6. The general linear group GLN over K has a subgroup which consists of all matrices which have determinant 1. And this is a subgroup because, first of all, the identity matrix has determinant 1, and also the determinant of the product is the product of the determinants. So if you have two matrices which have determinant 1, their product has determinant 1, and also if you have a matrix with determinant 1, the inverse to this matrix has determinant 1. So the special linear group SLNK, the group of all matrices with determinant 1, is a subgroup of GLNK. Here is a more complicated example. Consider R to the power n as a metric space in which the metric, so the distance between 2 points x and y, is given as follows. So it's a square root of x1 minus 1y squared plus x2 minus y2 squared plus and so on. Consider the symmetric group S on the set R to the power n. Denote by I R to the power n comma d the set consisting of all bijections from Rn to Rn which preserve the distance. In other words, we have a map F from Rn to Rn which is bijective and which has the properties that the distance between f of x and f of y is equal to the distance between x and y for all x and y in Rn. Such maps which preserve this distance, they are called isometries. Clearly the identity map is an isometry, and composition of isometries is an isometry, and the inverse of an isometry is an isometry. Therefore, this set of all isometries is a subgroup of the symmetric group SRn. Let us note that not all isometries are linear maps. So here is an example. If we fix some element y in R to the power n, then the map which sends an element x in R to the power n to x plus y, so it's a shift by y, this is obviously an isometry, because in this distance the shift by y disappears. But this map is linear only if y is equal to 0. So isometries, they are not necessarily linear map. There are linear map which are isometries, but also there are non-linear map which are isometries. Now we can use this example of a group of all isometries to define the so-called symmetries of geometric objects. Example 8. Consider the group of all isometries of the metric space R to the power n with respect to this Euclidean distance. Let x be some subset in R to the power n. Now we can consider the set g of x of all isometries which preserve x, so which means that f of x is equal to x as a set. Warning: this is not the same as asking for f of a to be equal to a for any element a in x. What we ask is that for any element a in x, f of a belongs to x, And also for any element b in X, there is c in X such that f of c is equal to b. So f sends X to itself bijectively. Clearly the identity map belongs to g of X, the composition of elements in g of X is in g of X, and the inverse of an element in g of X is an element in g of X. Therefore, g of X is a subgroup of the group of all isometries of R to the power n. So this is called the group of all symmetries of X. Trivial special cases: if X is empty or X is the whole of R to the power n, then g of X is the group of all isometries. Here are another special case, this case of so-called dihedral groups. Consider R to the power 2, so the real plane. And for an integer n, which is equal to 3, 4, 5, and so on, denote by xn the regular n-gon which is inscribed in the unit circle. Here is an example. If n is equal to 3, we have the following triangle inscribed in the unit circle. So we always assume that one of the vertices is the first basis vector 1, 0, and then we have the regular n-gon, in this case it's triangle, which is inscribed in the unit circle. Then the dihedral group D with the index 2n is defined as the group of symmetries of this regular n-gon xn. Since this is a regular polygon inscribed in a circle, the barycenter of this polygon is the center of the circle, which is the origin of our coordinate system. So this implies that any symmetry of xn, so any element in the dihedral group, is in fact a linear map from R2 to R2, because it preserves the origin. Next, let us talk about the intersection of subgroups. Let G be a group, and let Hi be a collection of subgroups of G indexed by some indexing set, capital I. Proposition: the intersection H of all these Hi's is a subgroup of G. Remark: if the capital I is the empty set, then by convention the intersection over the empty set is equal to the unit element in the group. That's our agreement. So let's prove this. So first note that if we take the identity element E, it belongs to all Hi, because all Hi are subgroups. So if we intersect all Hi, E belongs to this intersection, so E belongs to H. Next, if we have a pair of elements A and B which belong to all Hi at the same time, then the product of A and B belongs to all Hi, because all Hi are subgroups. Therefore, it belongs to the intersection of all Hi's. So H is closed with respect to the product. And finally, if we have an element which belongs to all Hi's, the inverse of this element also belongs to all Hi's, and so it belongs to the intersection. So the intersection of any number of subgroups is closed with respect to the identity element, with respect to the binary operation in the group, and with respect to taking inverses. So this means that the intersection of any number of subgroups of a fixed group is again a subgroup. We will use this property shortly. Let us discuss subgroups generated by a subset. Let G be a group and X a subset of G. Consider the subgroup, which is usually denoted by X in this kind of triangle brackets, which is defined as the intersection of all subgroups K in G which contain our set X. So this subgroup, so this is an intersection of subgroups, so it's a subgroup. We just proved this. This subgroup is called the subgroup of G generated by X. So note that if X is empty, then this subgroup is equal to E. So the subgroup generated by the empty set is just the identity element. By construction, the subgroup generated by some set is the smallest with respect to inclusion subgroup of G which contains that set. It is not very difficult to show that the subgroup generated by some set X coincides with a set of all elements in G, which can be written as a product A1, A2, and so on AK for some K, where each AI either belongs to X or the inverse of AI belongs to X. And note that due to the associativity of the group operation, it doesn't matter in which order we compute this long product. So the product A1, A2, and so on AK in any group doesn't depend on the order in which you multiply the elements in this product. So we can write it without brackets. Now we can talk about monogenic subgroups. So let G be a group and A an element in G. Then we have the corresponding monogenic subgroup. Monogenic means generated by one element, and that the subgroup generated by this element A. So this is the minimal subgroup of G, which contains the element A. Let us introduce the following notation. A to the power 0 is defined as the identity. For a positive integer n, A to the power n is defined as A times and so on times A, where this product contains exactly n factors. Similarly, for the negative integer n, A to the power n is defined as the product of minus n factors, each equal to A inverse. Claim the subgroup of G, which is generated by A, coincides with the set of all these elements A to the power n, where n is an integer. Proof. Clearly, the right-hand side is a subset of the left-hand side. The minimal subgroup containing A must contain all powers of A, it must contain the identity, and it must contain all powers of A inverse. On the other hand, multiplying A to the power I with A to the power j gives A to the power I plus j. It's very easy to show, and in particular the inverse of A to the power I is A to the power minus I, and this implies that the set of all elements A to the power n, where n is an integer, is indeed a subgroup. And this shows that the subgroup generated by A must be contained in this subgroup. So this is a subgroup, but it contains A, so definitely what is generated by A must be inside. And so they are equal. Great. Now we can use it to define the so-called order of an element in a group. Let G be a group and A an element in G. Definition: the order of A, usually denoted O of A, in G is defined as the cardinality of the subgroup of G generated by A. Proposition: if there exists a positive integer k such that A to the power k is E, then the minimal such positive integer coincides with the order of A. If such k doesn't exist, then the order of A is infinity. Proof: consider the elements A squared, A cubed, and so on. Assume first that they all are different. Then, none of these elements can equal to the identity, because as soon as A to some power k is equal to the identity, where k is a positive integer, then A to the power k plus 1 is equal to A to the power k times A. A to the power k is the identity, so it's E times A, so this is A, and this is equal to A to the power 1. So then we have two of these elements coinciding. Therefore, so they all are different, none of them is equal to E, and this means that the order of A is infinity. Now let us look at the opposite case. Assume that there are some positive integers I and j, with I strictly smaller than j, such that A to the power I is equal to A to the power j. If we multiply this with A to the power minus I, we will get the identity is equal to A to the power j minus I. And note that this j minus I is a positive integer now, by assumption. So now we can take k to be the minimal positive integer, such that A to the power k is equal to the identity. And now we can consider the elements e, a squared, and so on, a to the power k minus 1. And the same argument as above implies that all these elements should be different. Now we know that if I and j are elements between 0 and k minus 1, then the product of a to the power I and a to the power j is equal to a to the power m, where m is the unique number between 0 and k minus 1, which is congruent to I plus j modulo k. So in particular, A inverse is a to the power k minus 1, and so all these elements, they are closed with respect to the product and with respect to taking inverses. So they form a subgroup of G. So this means that the subgroup generated by A consists of exactly these elements, and so the order of the element A is exactly K, because these elements are different. Here are some examples. Example 1, the order of the identity in any group is 1. That's obvious. Example 2, the order of any non-zero element in the additive group of integers is infinity. That's because the subgroup generated by any non-zero element n just coincides with all integers divisible by n. This has infinitely many elements. Example 3, in the multiplicative group of all non-zero real numbers, the order of the identity 1 is 1. This is example 1. The order of minus 1 is 2. That's because minus 1 times minus 1 is 1, and that's all. And the order of any other element is infinity. If we have a non-zero real number which is not 1 or minus 1, and we take the powers of this number, we will have infinitely many real numbers. Similarly, example 4, in the group of all non-zero complex numbers, with respect to multiplication, the elements of finite order are exactly the roots of unity. Moreover, if xi is a primitive case root of unity, then the order of xi in the multiplicative group of non-zero complex numbers is exactly k. And the subgroup which is generated by this xi is exactly the subgroup in C star consisting of all kth roots of unity. One more example considers the dihedral group D2 times 3. Recall that that's a group of symmetries of the regular triangle inscribed into the unit circle in R2. So this group has 6 elements. The identity element, 2 rotations, so we can rotate this picture by the angle 2 pi over 3 or minus 2 pi over 3. And we have 3 reflections. So the triangle has 3 symmetry axes, the horizontal x, then this x, and this x. And we can reflect, make the mirror symmetry with respect to these symmetry axes. So the identity element has order 1. The identity element generates a trivial subgroup and hence has order 1. Any non-trivial rotation generates all rotations in the identity. So both non-trivial rotations have order 3. The subgroup generated by any non-trivial rotation is a subgroup of all rotations in the identity. The subgroup generated by any reflection just contains that reflection and the identity. The reflection squares to the identity. Hence all reflections have order 2. And it's a good exercise to check that this dihedral group has exactly 6 different subgroups. The identity subgroup, 3 two-element subgroups corresponding to the reflections, 1 3-element subgroup consisting of all rotations including the identity, and the whole group. Some problems and questions at the end. Problem question 1. Check with all details that Sx with respect to the composition of maps and with the identity map is a group. Problem question 2. Show that every isometry of any metric space is bijective. In particular of the metric space R to the power nd, it's bijective. Problem question 3. Prove with all details that the dihedral group D2 times n, the symmetries of a regular n-gon inscribed in a unit circle, has 2n elements. Problem question 4. Prove with all details that the subgroup generated by X coincides with the set of all elements in G, which can be written as products of elements in X or inverses of elements in X. And problem question 5. Prove with all details that a to the power I times a to the power j is equal to a to the power I plus j for all ij in Z. It's not totally trivial because here I and j can be negative, or one can be positive, another can be negative, so there is something to check here. Thank you very much and see you next time.